Hello, my name is Donald Bamber. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. The title of my talk is A New Axiomatization of Luce's Model of Choice and Ranking. My co-authors are I.R. Goodman and Hung Tien Nguyen. So let's talk about the choice task and the ranking task. Now, the agent that performs either of these tasks may be a person or an artificial intelligence device, etc. The choice universe for the task is a finite set denoted capital Omega. In the choice task, when shown any non-empty subset S of omega, the agent is required to choose the element of S that the agent most prefers. Here, S is called the choice set. In the ranking task, the agent is required to rank order the elements of omega in order of preference, beginning with the most preferred and ending with the least preferred. So let's talk about some notation for the choice task. Suppose that R is a subset of S is a subset of omega. This probability right here, which I'll call perch sub S of R, denotes the probability that the agent's most preferred member of S is in R. Notice the CH superscript here that indicates that that this probability measure has to do with choice. Now, perch sub S of R is an unconditional probability, not a conditional probability. Thus, we have a collection of probability measures for each choice set S. Perch sub S is a probability measure. So let's talk about Luce's choice axiom. As a reference, you could take a look at Luce's book, his 1959 book, Individual Choice Behavior. So Luce's choice axiom is the following. For sets R, a subset of S, a subset of T, a subset of omega, the probability that the agent's most preferred member of T is an R is equal to the probability, the product of the two probabilities, the probability that the most preferred element of T is in S times the probability that the most preferred element of S is in R. So we're going to need some notation now for the ranking task. Let ARO denote the agent's rank ordering of omega from most preferred to least preferred. ARO is a random permutation of omega. It's an n-tuple where n denotes the number of elements in omega. The probability of probability distribution of ARO is denoted by this probability here, which I'll call prank. Notice that the superscript RK in the notation, that indicates that the probability measure has to do with ranking. So if psi is any set of permutations of omega, then the probability that ARO is a member of psi is given by this notation right here. So, we're going to consider a case where choice is determined by ranking. So assume that the agent always has a preference ranking over the elements of omega. The axiom of rational choice states that when asked to choose an element from a choice set S, the agent first examines its preference ordering over omega, and then second chooses the element of S that is best ranked. Therefore, given the axiom of rational choice, the probability measure prank for ranking determines each of the probability measures perch sub S for choice. So here's a question of concern. For which ranking probability measures prank will the choice probability measures perch sub s satisfy Luce's choice axiom? The answer will turn out to be those pranks that satisfy the axiom of independence from the past, the IFP axiom, which we'll discuss. So this slide and the next two are not easy to absorb. You may want to pause the recording to further study each of these slides. So suppose that the agent is in the middle of stating its preference ranking over the elements of omega. So far we have heard the initial segment of the agent's rank ordering. Call the part that we have not yet heard the terminal segment. We know the identity of the items that will appear in the terminal segment. They are the elements of omega that did not appear in the initial segment. But we do not know the order in which they will appear. So here's an issue. Does knowing the order of elements in the initial segment help us predict the order of elements in the terminal segment? The IFP axiom says no. So let's consider some notation for the IFP axiom. Suppose that omega contains n elements. Let k be an integer from 1 to n minus 2. Suppose that S is a subset of omega containing k elements and that T is the set of elements of omega that are not in S. Because omega contains n elements, ARO is an n-tuple. Let begin sub k of ARO denote the k-tuple obtained by deleting all entries beyond the first k from the n-tuple ARO. And let array sub S ARO denote the n minus k tuple obtained by deleting from ARO all elements of S. So now we'll give a mathematical description of the IFP axiom. Let sigma and tau be any permutations of S and T respectively. The IFP axiom says that the events begin sub k of ARO equals sigma and array sub S of ARO equals tau are independent under the probability measure prank. Thus, the occurrence of the left event in equation 1 does not affect the probability of the right event occurring. If both events in one hold, then sigma is the initial segment of ARO and tau is the terminal segment. Thus, the IFP axiom implies that knowing the initial segment of ARO does not provide information about the order of entries in the terminal segment of ARO. So we can express Luce's choice axiom, or an equivalent to Luce's choice axiom, in terms of the new axioms. So assume that the axiom of rational choice holds. Then Luce's choice axiom holds if and only if the axiom of independence from the past holds. So can we formulate a mechanism for generating rankings that conform to the IFP axiom? Yes, to do that we'll use ideas based on Goodman and Wynn's work on product space conditional event algebra. So the iterated choice mechanism for rank ordering is explained in this slide. Suppose that the agent makes a sequence of choices C1, C2, C3, etc. from omega. Each choice is governed by the probability measure perch sub omega. So for each choice C sub I and each gamma an element of omega, perch sub omega of gamma is the probability that C sub I equals gamma. All the choices are all independent of each other. So with probability 1, each gamma in omega will appear somewhere in the sequence of choices. Now take the sequence of choices and for each gamma for each gamma in omega, erase all of its appearances except the first. The result is a permutation of omega. The probability distribution prank of those permutations conforms to the axiom of independence from the past. So here's an expression for the for a prank when it's generated by the iterated choice mechanism, and that's given by this equation right here, which you can read. Probability distributions having this form are known as the Plackett-Luce family of distributions. Plackett gave an informal justification for the family, and the family can also be derived from Luce's ranking postulate together with his choice axiom, but that's beyond the scope of this talk. Okay, that's the end of the talk. Thank you for your attention.